Okay, in this lecture 3, which is the last lecture of chapter 5, we are going to talk about the behavioral models, which it is the fourth type of system modeling. We talk the first one about the context diagram. Then we talk about the interactive diagram, and by the interactive, we talk about the use case and the sequence diagram. Then we went to the lecture 2, and we talk about the class diagram, the structural one. Then now the last model we have to conduct in this chapter or in any project, it is the behavioral. How the system behave. How the system behave in such a way if it meets or if it encounter a stimuli, an event, an input, how the system, how the program, how the function interact with that input, and where it goes, in which way. Behavioral model describe the internal dynamic aspects of an informal information system that support the business processes in an organization. Well, it depends on the business process, the business requirement. If the requirement it has a specific goal or whatever, the response of the system is go that way. During analysis, behavioral model describe what the internal logic of the processes without specifying how the process are to be implemented. In other words, the behavioral, it depends on the logic and the business rules which it comes in the business requirement. Of course, as we said, the topics we covered in the last two lectures, and this one, it is the context model, interaction model. Context model is the context diagram, interaction model, the use case and the sequence diagram, structural model, which it is represented by the class diagram, and the last models or the last prescription of the system modeling is the behavioral. And this, it goes to, we are going to the component and find out how the component behave if it encounter this input. It's a stimuli and response. And the last thing we are going to talk about in this lecture, it is the model-driven engineering, the last few slides, and we'll see what's going on with this. Well, behavioral models are model of a dynamic behavior of a system as it is executing. When we execute the program, how the program behave? Well, it depends on the input. The input, it is really the stimuli. It is the event, and the reaction of it is really the action, which it is, it depends on the input. They show what happens or what is supposed to happen when a system responds to a stimuli from its environment. You can think of these stimuli as being of two. The stimuli, it could be a data or an event. A data, if A greater than B, then. Or an event, like we are taking in this example, the microwave oven. When it is in the idle state, and then you put start, and then it will start, working. So it could be a data or event. Data, some data arrive that has to be processed by the system, or event, some event happen that triggers system processing. Event may be associated with data, although this is not always the case. Well, data-driven modeling, there are many business systems or data processing systems that are primarily driven by data. They are controlled by the data input to the system with relatively a little external event processing. Data-driven models show the sequence of action involved in processing input data and generating an associated output. They are particularly useful during the analysis of requirement, as they can be used to show end-to-end processing in that system. Well, in this diagram, we show an activity model of the insulin pump's operation. which it is, how this system act or react in such a way that, or the sequence of event it happens, in the system. First of all, we blood sugar sensor. When we draw the blood, and then we see the blood sugar sensor and how much, get the sensor value, how much, the sugar level. We get the sensor data, the number of it, and then we compute the sugar level, and we find, the blood sugar level, how much, calculate the insulin delivery or the insulin we need to encounter that level. Then we send it to the insulin requirement. We need 20 pieces, 20 cc, 10 cc, whatever. We calculate the pump command. Then after we calculate this one, it send it to the process, which it is calculate the pump command to send the command to the pump. Then the pump command control, it goes to the control pump, and then the insulin pump get it and inject it in the body of the person. So this is the sequence of event, which it goes, activity. It's like activity model. We start from blood sugar sensor, and we end up with the insulin pump when it's pumped the insulin in the body of a human. Here again, in the order processing example, we show the sequence of event. It occurs for the purchase order. The one start from the purchase office in the purchasing department until they send it to the supplier in order to the supplier to supply the company or the institution or whatever with that material. So first of all, they fill in the order. The order, they fill it electronically or, on paper. And then they send it to the purchasing department. Purchasing department there, they try to validate it, if it is really valid or not. If it is valid, then they go and see validation. It is really the items they order, is there is a budget for it or not, whatever. If everything is okay, it goes back to the system. Then they update the amount of the budget. Well, because they deduct the budget from that department, whatever, with the money or with the price of that order. Then after that, it goes back to the order and save it in the database order, in the order database, which it is, the purchasing database. Then from there, the order database, the program extract the information from the order database and send it to the supplier. So this one, it shows again the sequence the sequence of event it occurs from filling the order until they send it to the supplier. Event-driven modeling. Let's try to define what's really event-driven programming is. Event-driven programming is a programming logic or program or in which the flow of the program is determined by event, such as user action, like a mouse click, key, you press a key button, sensor, whatever, or a message from other program or threads. In here, we talk about it's a real-time system that are often event-driven within minimal data pricing. For example, a landline phone, a telephone in our houses, when it used to be a landline, not cellular, how to switch from respond to an event, such as a receiver of hook by generating a dial tone. Or the landline, when it receive a call and nobody answer it, it ring like 2-3 times, and then it switch to the message box. Event-driven models show how a system responds to external and internal event. It is based on the assumption that a system has a finite number of states. So because each of these are a state, we start always with the idle state. If there is an event occurs or happen, it will move to the state, to another state, which it is we talk about event, stimuli, and response. And event, so finite state and event, which it is stimuli, may cause a transition from one state to another. It depends on the value or what is really that event all about. Well, what's a state machine model or state chart? State machine diagrams typically are used to describe state-dependent behavior for an object. An object responds differently to the same event depending on what state it is in. These model the behavior of the system in response to external and internal events. They show the system responses to stimuli, so are often used for modeling real-time system. State machine model shows system state as node and event as arc between these nodes. When an event occurs, the system moves from one state to another. State charts are an integral, which it is an important part of unified modeling language and are used to represent the state machine model. So state machine model, behavioral diagram, state transition diagram, all of them, they have the same thing, while they are synonyms of each other. Well, let's look at the state diagram of a microwave oven. Microwave oven, usually you go to the kitchen and you find the microwave oven at waiting state. So that's what the node start there, and then you see the process sitting there like in a waiting state. It's an idle state. If you don't touch it, it won't move to another state. But if you wanna try to cook something in that microwave, you're gonna turn it either to a full power or half power. Some of them designed for, some microwave designed for this way. It's a full power, 600 watt or 300. You push the full power, it moves from the idle waiting state to the full power. If you push the half a power, then it go to the other one half power, 300 watt. Now, let's assume that really you are in the full power and oops, no, I forget, I think I wanna really cook, I wanna move it really to the 300, then you could really click there and from full power, and that's what you see, and then it goes to the half power. Then after that, if it is a full power or a power, then you put the timer. You see how much, 50 seconds, 30 seconds, a minute, whatever it is, and then it goes to the set time. Actually with timer, and then you go to the set time. Then you put 50, 60 minutes, whatever, and you push start. When you push start, see the time, which it's like the number where it goes to the state. It goes back to the state. When you set the time, you put 100 seconds, 100, and that's it. Then after that, you try to cook, to see if it's gonna start or not. If you want to start it and the door closed, it will go to the enable state, which will let you go and start cooking. Otherwise, if it is open and the time is set, it's going to be disabled. So from disable, you have to close the door to enable it. You enable it, so you go from disable to enable, then after that start. Then you go and you operate and start working, and from operate, you find if somebody opened the door, it will go to the disable as, a security measure, a safety measure. If you cancel it, and then it go to the wait state. So you could see from the operation state, then if you cancel it, if you push the cancel, it will go to the waiting state and display the time, whatever. Or if you leave it until the time ends, then again, when it is done, the buzzer comes on and then it go again to the waiting state. But if you want to see the operation state down, we could find out that there probably could be more state and more action there. So we could really take that operation and decompose it to many states, as we're gonna see next time. So let's assume that really you have a question to construct a state chart. So what is really the way of doing this. First of all, we have to find the states. What are really the states? For the microwave oven, this example, the one we just talked about in the previous slide, we have a state, waiting state, which is the first state. You see it, it's putting an oval there. The half power, when you push the half power, it goes to the half power state. So the half power is the stimuli and the state. And the full power, again, it is stimuli, it is an event and the state as we saw it in the previous slide. Then set time. You see when you set the time and it is like recursive 1, you put the second 100, 100 as we said. Disable, then disable state, oven operation is disabled, like a safety precaution as we said. It's not ready. Why? Because the door is open, whatever. Then enable, the door closed, the time is set and ready to go. And operation, oven is in operation and the light is on and the timetable is working. Everything is okay until we see what's really gonna happen with that operation. As we said, in the previous, we could, wait until the time is gone off, and then after that the buzzer is sounded, or if we hit cancel, again it go to disable state. Then in the previous slide, we put all the state in that system. Now we're gonna see what event, what stimuli are there in them. Half power, as we said before, half power is the stimuli and is this state. Full power, it is a stimuli and the state. Timer passed for the time buttons. The number has presented in a numeric. You put the number. Door open, door closed, start and cancel. Those are the stimuli. Those are the event which it is in that system. We put the state and then we put the stimuli and then we could see the sequence of event. What is really the stimuli and then what's the response of it, and we could really draw the state chart from there. As we said early in the previous slides, the operation state, it could have again many different operations. It could have many different operations, like checking the status, cook, done, and alarm. But the one it goes off that state, you see as it is disabled. Or if the door open is go to disable, or you cancel, it goes to waiting. If somebody opened the microwave while it is running, it will go right away to disable. It will stop. But if you leave it until it is done and you hit cancel twice or one time, it depends on the design of the microwave, it will go to the waiting state. There are 4 states here. Check the status. If the turntable fault, if anything in the turntable, or emitter fault, any fault it happens there, the alarm, it goes off and then it goes to disable. If everything okay in the checking, then it go to the cook and the time it go down from 50, 49, 48, 47 until it gets 0. If everything is okay and it gets 0 whatever, then it will finish, it give you the buzzer, done, time out, it go to the done state, buzzer for a few seconds, 2 seconds, 3 seconds, whatever, it depends on the design, then it go to the win state. But while it's cooking, if you hit cancel, as you see, again it go to the waiting state. Model-driven engineering. What's really model-driven engineering? It is a software development methodology that saves businesses a significant amount of time and money and enable them to streamline, to sequence their operation, with all the parties working together with a single model. Model-driven engineering improves coordination between the various stakeholders, resulting in more robust software solution with fewer bugs. Model-driven engineering, MDE, is an approach to software development where model rather than programs are the principal output of the development process. Not really program, not operation as we see, but the model. Software where the models rather than the programs are the input for it. The programs that execute on a hardware software platform are then generated automatically from the model. In other words, we're gonna model the models. In other words, the MDE, the software development, where the model rather than the program are the input of the development process. The program, the respondent or proponents of the MDE, the people who against that one, argue that this raises the level of abstraction in a software engineering, so that the engineers no longer have to be concerned with the programming language detail or the specifics of execution platform. Well, this is still new, and I believe there are more abstraction in the model-driven engineering. Model-driven engineering is still an early stage of development, and it is unclear whether or not it will have a significant effect in a software engineering practice. Well, the people divide here into different streams. One of them is with the model-driven engineering, one against it. The people with it, the people they think that it is really a great methodology to use. They're saying this methodology allows system to consider at high level of abstraction. The system, you look at the system in high level abstraction. But we know the abstraction, you know how bad it is from the user requirement, because it takes many different interpretation. When you abstract something, it's not clear of what really you are doing in there. But here they consider it as really advantage of it. The pros, they saying generating code automatically means that it is cheaper to adapt system to a new platform. It's quicker, cheaper. And in this case, probably they don't need programmer anymore. But the people who are against this one, they're saying model for abstraction are not necessarily right for implementation. Why? Because with abstraction, there is a lot of ambiguity. There is a lot of not clear things, which is the same problem of the natural language when we said the clarification, ambiguity. And why? Because it is an abstract. In abstract, it means, when somebody gives you an abstract thing or whatever, I think it depends on your interpretation to it, because there is no detail and that abstraction. And saving from generating code may be outweighed by the cost of developing. Well, they're saying that we're going to save the code because we have code generating code automatically. That's what the pro said. But they're saying here, generating code automatically, it needs really interpreter. It needs something like, compiler. You need to take, this model and those, I think it will take a long time in order to develop them. So saving from generating code may be outweighed by the cost of developing translator for a new platform. Okay, to make an abstraction of the whole chapter 5, which is the last 3 lectures. First of all, we talk about the model. What's a model? We said a model is an abstract view of a system that ignores system detail. Complementary models can be developed to show the system context, interaction, structure, and behavior. And these are really the 4 prescription, the 4 type of models really we did in the last 3 chapters. We talk about context model, which it show how a system that's being modeled is positioned in environment. What's really the boundary, the system boundary. Then we talk about the use case diagram and sequence diagram as interactive between user and systems in the system being designed. Use case describe interaction between a system and external actors. Sequence diagram are more information to these by showing interaction between system object between component and component, between object and object. Then we went there to the structural model, which is the organization and architecture of a system. And that one is the class diagram, which is used to define the static structure of classes in a system and their association. We show the major entities, the major entity of the system, which is those classes. Then we cover the behavioral model, which is used to describe the dynamic behavior of an executing system. Behavior can be modeled from the perspective of a data processed by the system or by the event, as we said. Active diagram may be used to model the processing of data where each activity represents the process. And then we went there and we look at the state diagram, state chart diagram, the behavioral diagram, state transition diagram, whatever, which is used to model system behavior in response to internal or external event. Finally, we talk a little thing, the last two slides, in a model-driven engineering, which is an approach of software development in which system is represented as a set of models that can be automatically transformed to an executable code. By this, we finish chapter 5, and then in the next lecture, we'll go to chapter 6, which it is architecture design. Thanks, and bye.